Hi folks, it's Mr. Moodledge here. This time, this is a preliminary video on stuff you should know coming into MCR3U from grade 9 and 10 and so on. Some of the basics. So the plan here is I have my annotated notes from class today, and the completed note, I just wanted to go over it and kind of voice it over how I got the answers and the solution, okay? Just so you can review and if you need to on your own. I'm going to try to keep this a little short, so 10 minutes. We'll see how we go, right? All right, so polynomial stuff, simplify the following. So simplify means you start with these types of long expressions, try to reduce it down as much as possible, expand, get rid of brackets, and so on. So in the beginning, we're distributing this 2 here into everything inside the bracket. So that's how we get 2x minus 6 here. You're just multiplying by 2 each of the terms inside, and here multiplying each of the terms by 4. It's 28 minus 8x, and then you combine like terms. So 2x and negative 8x gives negative 6x, and then these two terms combine to give positive 22. Okay. When you have something like this is a binomial times a binomial. You're using the distributive property, so FOIL, first, outer, inner, last. And then you get something like this, and then again, you collect like terms. So here, you're combining the two middle terms to get negative 10a. Okay. When we get something like this, we're just applying, again, this is a monomial times a binomial, so we're distributing that into each term. So negative 2x times x is negative 2x squared, because x times x is x squared. And then negative 2x times negative 5, two negatives become positive when they're multiplied. 2 times 5 is 10, and then you just have an x. Negative 3x times 4 is negative 12x. Negative 3x times negative 2x is positive 6x squared, okay? And then I can look for like terms, so I got a negative 2x squared, 6x squared. I can combine them to give 4x squared positive. And then here, these two combine because they both have an x, they're like terms, to give negative 2x. All right, so that's the gist of simplifying. Next, we move into solving equations. If I take a look at this one right here, the idea is getting all the variables on one side of the equation, and well, this is a one variable equation, getting the variable on one side of the equation and getting the constants on the other. So here I have, again, you can think of it as moving across the equal sign. So here I want to get all my x things, let's say, to the right side. I can choose left or right, but let's say in this case I want to move it to the right here so that I end up with a positive coefficient for x. So here 3x. So I'm going to subtract 2x from both sides essentially, and then I get 3x on the right side. Had I moved the 5x to this side, I would have ended up with negative 3x, right? I would have ended up with negative 3x on the left, and then I would have ended up with positive 4 on the right. And so I'd end up with the same answer, but you know, it's just I prefer to divide by a positive answer coefficient. That's completely up to you though. So at the end of the day, I ended up with x is negative 4 over 3. Okay. This is an example of a question where you want to simplify first. So hence the reason we did this part right here. You want to simplify that type of thing first, collect like terms, get it into a format where it's like this. So then it's like question 2a here, and then collect like terms, bring all the x terms into the one side and the numbers into the other, constants to the other side. So here I brought, in this case, 12x, negative 12x to that side, so added 12x to both sides. So I got 13x on the left side, and then this constant here, I moved to the other side by subtracting, so I get 2 on the right side, and then I can divide out 13 from both sides to isolate for x. So x is 2 over 13. Good. Moving on. So this question is actually really interesting because there's there's 3 ways to go about this, 3 methods. Method 1 is right here. So getting rid of the denominator. What that means is we're trying to find what is the lowest common multiple of 3, this invisible 1 here, and 5. So that's 15. And so I'm going to multiply everything, all the terms by 15. And essentially, I'm getting rid of the denominators. Because whatever I do to one side of the equation, as long as I do to the other side, it's fine. So then I get, and I simplify, I get something like this. And now that just becomes like the previous question. I can collect the like terms. 25x is equal to 12. And then x is equal to 12 over 25. Okay, so that's method 1, if you prefer that. Method 2 is very much similar, but in this case, instead of multiplying both sides by 15, I multiply each side. So I want to make the denominator 15, but I'm changing each fraction one by one. So it's kind of like the same thing, but in this case, I keep the denominators, but I just multiply the top and bottom of each fraction by that greatest common, so that lowest common multiple, or so that great, yeah, so I'm trying to get it to that lowest common multiple, so I'm multiplying 3 by 5, and then 2x by 5. And likewise for 1, how do I get to 15? Well, I'll multiply both top but bottom by 15, and I have to multiply the top by 15. 5 to get to 15, multiply by 3, and then the 4 multiplied by 3, right? In a sense, when in a nutshell, when I do this, I get something like this. And when the denominators are the same, I can equate the numerators. So now I just get back to the method 1. I get this, and then I can add those together to get 25x equal 12, and then easy from there. Okay. Method 3, there is another method. Again, you don't. It's not the purpose of this is not to memorize the method, but to realize there's more than one way to solve this. Is what we call cross multiplying. So you're simplifying the left side. Essentially, I can't add these two fractions unless the denominators are the same. So let's make the denominator of the second term a 3. So multiply the bottom and top by 3. So I get 3x over 3. Everything else was kept the same. Now I can add these two fractions to get 5x over 3 and is equal to 4 or 5. Now I can cross multiply. Essentially, I multiply 5 by 5x, so 25x is equal to 12. And then now divide by 25. So x is equal to 12 over 25. So in each case, I get the same answer, and that's good. Okay, so that's a good question to try. D, this is using like the zero property. So this is in factored form. This is a quadratic equation in factored form. So essentially, I set each factor equal to 0. So one solution is x minus 3 is equal to 0. So that happens when x is equal to 3. Or this is equal to 0 when 2x plus 1 is equal to 0 when I just isolate for x, subtract -1 and divide by 2. So x is equal to -1/2. All right, that works out nicely. Here we get something where it's, so down here, this is in standard form. I want to factor this. I want to get it into factored form. So I'm going to use the man method, two numbers that multiply to give -14 and add to give -5. So those two numbers are -7 and +2. And so I write them like this, x minus 7, x plus 2, and now it's just the zero property. So x is equal to 7, x is equal to -2. Those two numbers will make each of these 0, hence they're the solutions. Okay, and that's how we solve those types of equations. All right, now we can get to the third component, which is quadratics. So this kind of stuff is given a quadratic, looking at the transformations that happens to y equals x squared, and then identifying, I just noticed this now, identifying the vertex. Okay, so in this case, the vertical, so we're looking at this number right here, it's a 3 in front of the x squared. So that signifies that we have a vertical stretch, right? Whenever this number is bigger than 1, it's always going to be a stretch, a vertical stretch, and it's by a factor of 3 because that number is 3. If that number is between 0 and 1, like here, we call it a compression. So this is a compression, a vertical compression by a factor of 1/3. And the negative just means that it's reflected on the x-axis. The +5 at the end means that there's a shift of 5 units up. In this case, I would say that the vertex is equal to 0, 0, because if you think about this a little bit more from grade 10, I could write this in vertex form, kind of like this, +0. This is like my h and my k, so those are my vertex. Clearly, they're 0, 0, right? Like all I had to do to x squared to get to this is just stretch it by a factor of 3. It didn't move up or down, so the vertex stays 0, 0. Here, I first I reflected it, and then I compressed it by a factor of 1/3, so it got like shorter, I guess, relatively speaking, compared to this. And then I shifted it up by 5. So from that, analogy, the vertex now becomes 0, comma 5. Okay, so that's how that works. Yeah, okay, and it's opening down because it's a negative here. And this one is opening up because it's positive. Okay, cool. All right, and then moving on to the last section. So we're just a little bit over 10 minutes, but the last section here is sketching the graphs of the following. So stuff like this. This is linear. Whenever you see something like this, always think back to grade 9, y equals mx plus b. M is the slope and b is the y-intercept. So always start with the y-intercept, 1. Put a dot at y equals 1 right there. And then the slope, really, you can think of it as if it's just a number like 3, an integer. You think of it as a fraction, 3 over 1, because that's nice, because then the 3 is the rise and the 1 is the run. So from 1, I'm just going up 3, 1, 2, 3, and then 1 to the right. And then I just do that again, 1, 2, 3, 1 to the right. And I end up at my other point, and I can now connect the dots that way. So that's how I graph a linear relation there. And then here, when we have a quadratic, we'll start by realizing that, y equals x squared. That's the, parent quadratic, like the most basic one. It looks like this. If you forget the table of values, every x value is squared. So negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. I just drew that here for reference. The vertex is 0, 0. Now, what's happening here is you can think of it as in terms of transformations. I stretch it by a factor of 2, and then it moves 3 to the right, 5 up. You could do it that way. Or you could realize that, the vertex is now clearly 3, 5, because this is what's vertex form of a quadratic looks like. It's HK, so vertex is 3, 5, put a dot there. And then if you remember the step pattern, I'm just going a little bit further here into grade 10, but the step pattern, this is like a shortcut for drawing quadratics, just like the shortcut for drawing linear stuff is rise over run and, going up this way and then that way, 3 up, 1 right, 3 up, 1 right. The trick here is the step pattern for normal, like a x squared, y equals x squared is just 1, 3, 5. But now, so this is for x squared. Now the step pattern for something that's like 2x squared, well, I just take this same pattern and I multiply it by 2. So times 2, times 2, times 2, each one. Sorry, that looks like 2 squared, x squared, but I'll just here say times 2, star 2, star 2, star 2. And so I get my new step pattern for 2x squared is going to be 2, 6, 10. Okay, so hence, what that means is I start at the vertex, dot, and then I go 1 right, 2 up now, instead of 1 right, 1 up. Because here it was 1 right, 1 up, and 1 right, 3 up, and so on like that. 1 left, 3 up, and so on. But here, I would have continued if I'd go 1 left, 5 up, and that would give me the next point. But here it's just 1 right, 2 up, 1 right, 6 up, but I don't have enough space for 6, so I just leave it like that. Okay, that's how I do it. That is the end of this video. I know it's a quick summary. You can slow it down if you want, rewatch it. Let me know if you have any questions. Thank you. Here is the homework from the Nelson Functions 11 textbook. Go ahead and do those now. All right. Thank you. Until next time.